Okay. So yes, I am not teaching you through the laptop because my stylus broke, and at last, right? So you know that we're having so much problem, right? So for some time, for a while, I'll be teaching through the cameras only. Okay, fine. So it's good, right? It's good after seeing me, like, seeing me after a long time, right? Okay, fine. So we will start. So we have a 2 hour session, right? As you all know, 6 to 8, right? Well, I'll give you a 10 minutes break in between. Okay, say by 7 o'clock, I'll give you a break. We'll again start by 7:10, and I'll finish by 8:10. Is that cool? Right? Okay.
Sir,
Yeah.
could you give a small recap of last class alone? Like a small brush up
Yeah,
of
yeah, sure.
hyperconjugation.
No, I think I thought resonance, not hyperconjugation, right? Did you check in the video? I think it was last class was resonance. We spoke about
I
benzene.
checked the first half of the video, it was about hyperconjugation, sir.
Okay, okay, fine, cool. I can do it. Not a big deal. Right. So quickly going through that, right? So hyperconjugation, right? So hyperconjugation is also called as sigma bond resonance, right? So hyperconjugation is also called as sigma bond resonance. So generally we say that sigma bonds are not going to involve in resonance, right? We only take pi electrons and shift them, right? So, but in hyperconjugation, it's actually going to be a sigma bonds that are going to involve in resonance. Right. Okay. Now, what are all the conditions for hyperconjugation to happen? First condition is that it'll be applicable only to carbocations and free radicals. Right. Now, the reason is I should have an empty orbital. Both of them are sp2 hybridized. Right. So one of the p orbital will be empty. Right. So obviously, for the bond to get shifted to the carbocation or carbanion, I mean to any carbon atom for that matter, I should have some empty orbital which can accommodate the electrons. That is one thing. Second thing is that not all, we are talking about sigma bonds, right? But not all sigma bonds are capable of undergoing hyperconjugation. It is only the CH sigma bond which is capable of undergoing hyperconjugation, right? So if that's the case, I should have at least one alpha hydrogen to be present for hyperconjugation to happen. Okay, right. And the thing is, so now please understand that the number of alpha hydrogens, right, is equal to the number of hyperconjugating structures, right? And obviously, more and more is the hyperconjugation, more and more is the stability of the species, right? So these are all the things which you need to know, right? So let me take an example. Say, for example, if I have CH3CH2 dot, right? Now you see this is the main carbon atom. So this is the carbon atom which is in my alpha position, right? So do I have a hydrogen atom here? Yes, I have a hydrogen atom here, right? So what is going to happen is this hydrogen is going to come out as H plus, okay? And obviously this bond is going to go here, making sure that I'm going to get a H plus, right? So what will happen is I will be writing the structure like this. CH2 is a double bond CH2, and somewhere here I'm going to have a H plus. Okay, now this is one of the hyperconjugating structures. As I told you, as many number of alpha hydrogens I'm going to have, that many number of hyperconjugating structures. So in this case, I have 3 hyperconjugating structures because I have 3 alpha hydrogen. One of them is this, 2 more are here. 3 alpha hydrogens, 3 hyperconjugating structures. Right. Okay. Now, if at all I go for secondary, say for example, if I had CH3, CH dot CH3, right? Now, both these carbon atoms are alpha carbon atoms. Now, how many hyperconjugations will come? 6 hyperconjugations will come because I have 3 plus 3, 6 number of alpha hydrogens. Right. So as I told you, more and more hyperconjugating structures, more and more stability. So when I compare a primary free radical with a secondary free radical is more stable. And obviously, if you go for a tertiary free radical, that is going to have still more number of hyperconjugated structures. If you just remove this hydrogen and put a CH3, now you will find that they're going to have 9 hyperconjugated structures. So obviously, remember, for free radical stability, the order of stability is tertiary is greater than secondary, greater than primary. Okay, now this is what is my order of stability for free radicals, right? Now, same thing if you had for carbocation, right? If instead of this dot, if we had a plus sign, carbocation, same thing holds good, because that is also going to be sp2 hybridized, right? Okay, so again, if you do the same thing, you already know what is the order of stability of carbocations with respect to inductive effect. You know that it is going to be tertiary, secondary, and primary. Same thing you will get for same result you will get using hyperconjugation also, right? So that is about hyperconjugation. Is it okay?
Okay, so understood.
Right. Okay. So we were talking about resonance, people, if you can remember last class, right? We looked into the resonance structure of benzene, and I told you that say if I have something like this, right? Say if I go for resonance, right? We know how are we going to define it? It is the movement or delocalization of pi electrons. Okay, it is the movement or delocalization of pi electrons, and we know what all can be the pi electrons. Quickly tell me, what and all can be pi electrons? What and all can be pi electrons? What do you mean by pi electrons?
So electrons in pi bond.
Okay, then?
And lone pairs.
Okay.
And negative charge.
Absolutely. Right. So all these things, all these three things can be regarded as pi electrons. Right. Okay. So I will take I'll take benzene as the example, or any benzene derivative as an example. Right. Like if I take, for example, this one, say I have OCH3, right, and say I have benzene ring, right? Now it's always better to start the resonance structure from the lone pair or the negative charge. If we don't have that, then you start with the pi bond, right? So now what will happen? This can come here. Okay, now this bond can go here, right? That's the first resonance structure. So now what will you have? I have double bond O CH3, and the oxygen atom should have a positive charge because it has lost its lone pair, right? And this bond has broken. So you will have a negative charge here, and the rest of the thing stays, right? Now you can actually skip this step, right? Now, because what will happen is this will come here, and actually this will come here, again make a negative charge, right? So now you can bring this step directly. What you can do is, instead of breaking it, put a negative charge and then making a bond here, right? You can actually directly do this. You can directly do it like OCH3 plus, I can directly put it and say I will be able to put a negative charge directly. So either way, right? So if at all you are confused with this, do not go for it, right? So what will be the next resonance structure? The next resonance structure would have been OCH3 plus. Now I have a bond here, there is a negative charge here, and there's a bond here, right? And say now this will go here, and this bond will break. The next structure, right? Next structure would be a bond here, a double bond OCH3 with a positive charge, and this bond has gone over here, and there is a bond here, right? Okay, and last what will happen? This will come here, this will go back to oxygen. So the last structure is gonna look like this. OCH3, the positive charge is gone because it has gone back. Now you have a bond here, you have a bond here, and you have a bond here. Right? So you see, so this is how I write my resonance structure. We spent good amount of time in solving all of these, right? We took OH, maybe NH2. So remember, right? So these, now whenever you see that the electron cloud is moving towards carbon, right? Though that particular resonance effect is what is called as plus R effect. if the electron density on carbon, if it increases, right? Now remember, electron donating groups plus R effect will be given by electron donating groups like OH. Like what can be examples of electron donating? Say for example, I can have OH, NH2, OR. R is an alkyl group. In this case, it's OCH3, right? So all these things are going to be my electron donating groups, and they will definitely give me plus R effect in the sense that they will increase the electron density on the carbon, right? Now, can you give me any example for electron withdrawing group, which will give me minus R effect with respect to benzene? What example we saw? Do you remember? Something will give me, we saw one example for minus R effect. So obviously that is going to be an electron withdrawing group. What was that group?
So nitrogen.
Nitrogen, or what is it? Nitrogen. Here also I have nitrogen. NH2 is also there, nitrogen. What group exactly? What function group? Nobody remembers. It's NO2, nitro group, right? So I think everybody forgot everything, right? So like guys, if you have taken this down, I can rub this part. Have you taken this down? Is it done?
Yes, sir.
Okay, fine. Right. Say if I had nitro group, right? Now this nitrogen doesn't have any lone pair, so it cannot donate the lone pair to the benzene ring. That is not possible. So what is going to happen is it is going to behave as an electron withdrawing group. So what is going to happen is this bond will go here and this bond will break. That's the first step, right? Now what will happen to this? So now I would have had a double bond O and O minus, and a coordinate bond is there. That is fine. And there is no bond. Now see, this carbon atom has lost electrons, right? So there will be a positive charge. Done, right? Next, what will happen? Now this bond can directly go here, right? So now, or you break it, make a negative charge, and the next step you make the bond. Either way, you're going to get the same thing, right? So now I would have had double bond N O minus coordinate bond. Now you would have a bond here, and this carbon now has lost electron, so you'll put a positive charge here. What will be the next step? Now this bond will come here, right? Now I have a bond here, I have a bond here, and this carbon atom will get the positive charge. Now the last step would be this will come here and this bond can go here. Correct, right? So at last, I will be having a bond here, a single bond, double bond O, and this thing, I have a bond here and a bond here. So these are all the resonance structure for nitrobenzene. Okay, guys, you have to read, this is very, very important, right? If at all you want to understand how reactions happen with respect to this, that will come in the next chapter, hydrocarbons. Okay, so these are all very, 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 very important. Where you form the positive charge, where you form the negative charge if I have an electron donating group, right? All these matters. Okay, fine. So you easily understand that this is how the resonance structures of nitrobenzene is going to occur. Okay, right. Now, can you tell me any other electron withdrawing group? Like with respect to benzene, nitrobenzene is one. NO2 group is going to be an electron withdrawing group. It is going to give me minus R effect. Right? So like that, can you tell me any other group? What do you think? Any other functional group can you think of? A benzene ring attached to some functional group. any other thing which will give me this kind of effect, minus R effect. Any guesses?
Aldehyde groups.
Good, good.
Acids.
Yes, acids, yes, that will also work. Right. So do me a favor, right? Take a, I think, hope everybody has a notebook and a pen with you. Go for benzaldehyde. I think I gave it as homework. I don't know whether you did it, right? So take benzaldehyde, basically benzene ring with a CHO, and try to draw the resonance structures. Quick, 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 go for it. I'll give you 2-3 minutes time. So please understand, if the group attached to the benzene ring, if it has a lone pair, then it is going to be an electron donating group. If it doesn't have any lone pair, then definitely it is going to be an electron withdrawing group. And these kind of structures is what you will get. Right? Go for it. Take benzaldehyde. Or you can even take acetophenone, but it's not going to matter much. So I had a C double bond O. So you can even put H, or you can even put a R, anything. So let me take benzaldehyde. So this is my structure. Benzaldehyde is the structure. Now go for it. Right? Draw the resonance structures. Right? So if you're, I think most of you are using your phone for attending the classes. Is that correct? Or is there anyone who's using a laptop?
I'm using laptop, sir.
Okay, no issues.
I'm using laptop.
No issues, no issues. So what you do is, after finishing the resonance structure, you have my WhatsApp number. So send a personal text WhatsApp to me. After finishing it, take a picture and send it to me. I want everybody to do it. I can see who one are here. So Divya,
I
Rahul.
have a doubt.
Sorry.
So I have a doubt actually.
1 second. So I have Rohan, Divya, Rahul, Mithun Krishna, Shruti, and Suryamatu. Right. So I want it. It doesn't matter, guys, if you're gonna do it correctly or not. But I want to see where you're doing the mistake. So I'll give you 2-3 minutes maximum time. Draw the resonance structure and send it to me in WhatsApp personally. Don't put it in the group. Right? Send it to me personally. Yes, Rohan, tell me about it.
The first double bond, like in the previous example, sir, like nitrobenzene, the double bond from oxygen becomes O minus, right, sir?
Yeah, correct.
What causes it, sir?
Okay. See, that is heterolytic cleavage, correct? Say, for example, say I have something, say I have a C double bond O, something, right? Okay. Now, if I break the bond, if I break the pi bond heterolytically, right, what will happen? That means this carbon has lost electrons, and this obviously more electronegative atom will gain the electrons. So
Yes.
if I break a bond like this, what will happen? I will have carbon to have a positive charge, oxygen to have a negative charge. This exact same thing.
Okay,
is
sir, I understood. Sir.
Right. Now, why am I not putting a positive charge on that nitrogen? Is because one bond was broken and another bond was formed simultaneously. Hope you understand. When double bond O, one bond was broken, another bond is coming from the benzene.
Yes, sir. I understood.
Okay. Yeah. Okay. I'm going to call people. Just give me a yes. I just want to confirm whether everybody is there. Divya, are you there? Divya?
Yes, sir.
Oh, you're there. Okay. Rahul? Okay, you're there. Rohan is there. Mithun, are you there? Mithun? Okay. Shruti is there, I know. Surya, are you there?
Yes, sir. I'm there.
Okay, good. So whomever told me yes. Yeah, whomever told me yes, please send it.
Sir, I'm using laptop, sir. I don't have my mobile here.
You don't have your mobile phone?
Yes, sir.
Oh, okay, fine. But at least try it. Don't sit idle. Yeah. Who is number 81488?
That's me, sir.
Kana, I gave you for this structure, but what you have drawn is for phenol.
Yes, sir.
Can you please check? This is for CHO, but what you have sent me is for OH. Yeah, but what you have done is there. What done there is correct. Okay, right. But that is not the question. Okay, another one.
Sensor.
Yeah, just saw. Okay. Okay, Rohan, what you sent is okay. Fine, correct. Okay, fine. So I think we have taken enough amount of time. Okay, it's pretty simple. Exactly what it did in case of nitrobenzene, the exact same thing you will do, right? So you will start either from this bond or you can start from this bond. One more picture I got once. So yes, correct. Who I don't know who was it? 9600. Who is it?
This is Shruti, sir.
Okay, sure. Oh, then whose is that number 81488? That is also yours.
That's mine, sir.
Oh, Divya's. Okay, Divya. Fine. Right. Okay. So yeah, I think most of you would have gotten it right. It's going to be exactly similar to the previous case. So you will start from here and you'll break this bond. You will have double bond CO minus and a H, and you will form a positive charge, and this, and this will come. The next structure will be CO minus and a H. Now there'll be a bond here, a positive charge here, and this bond here, and this will come. H, a bond here, a bond here, a positive charge here. Now the last step, this will come. Oh, that's a double bond. Sorry. Right now, this will come, and this bond will go here. So the last structure I have C double bond O and a H, a bond here, a bond here, and a bond here. Yes, this would be my structure. Okay, fine. So we understood. And even if this was COCH3 or C double bond O OH, anything with a C double bond O will always be an electron withdrawing group, giving me minus R. Okay, right? Fine. That is about benzene rings' resonance structures. Okay. Now, obviously, more and more is the amount of resonance structure, more and more will be the stability. Okay. Now, how will I prove? Like, there is nothing to prove in the sense that wherever you see the charge is not going to be in one place, right? That actually creates more entropy, right? And I don't know whether you have studied in, you must remember from thermodynamics. For a spontaneous process, for me to attain stability, the entropy has to increase. Okay, so because the charges are moving in resonance, right? It brings in more stability. Sorry, it brings in more entropy, thereby bringing more stability. Okay, fine. So more and more resonance structures, more and more of the stability. That you have to understand. Okay, now I will be these are the resonance structures. Now I'll be able to use it. I'll be able to use it in certain cases to say that yeah, that carbocation is stable, or say this carbanion is stable, or I can say that this is more acidic, this is less acidic, this is more basic, less basic. All these things can be told. Okay, right. So we'll spend some time on that. How do you decide? We'll take some cases. Okay. Right. Say I have a structure like this: CH2 double bond, CH, CH2, OH, something like this. Or will it work? No, will it not work? Something like this I have. Okay, now I want to know, or I'll just compare it with this. Okay, right? So I sorry, I want to know which is going to be a better acid. Obviously, I know alcohols, as I told you, are acidic in nature. Right. Okay. Now, how will I do it? You have to go for the stability of the conjugate base. Correct. You have to go for stability of the conjugate base. Right. So what you have to do for that? You have to remove the H plus from both of them. O minus, O minus. Right. And out of these two, whichever is more stable, that particular acid would have been a stronger acid. Right. Now here, you don't have anything else other than the inductive effect. I know alkyl groups are going to be inductive effect, so I'm going to increase the negative charge on the oxygen, thereby it is destabilized, right? But if I go here, or you can tell that, sir, yeah, I have some what is that? I have alkyl groups present, which is going to increase the negative charge. Yes, I don't deny that, but what you have to see is I can have resonance happen. This will come and this will break. Is it not? I have a negative charge that will make a double bond, and that bond will break because this carbon cannot have 5 bonds. So I can write the resonance structure like this: CH2 minus CH double bond O CH3. Right. This is exactly what we did in tautomycin, if you can remember. Right. This is the enol form, and that would have been the keto form. Right. Okay. So obviously I can say that this will be a better acid than this because it has resonance, but this doesn't have any resonance. More and more resonance structure, more and more stability.
Okay.
Okay, right? Any doubts? Someone said something?
Understood, sir.
Okay, fine. So I can give you more examples. Right. Say, OH, another OH. Say I have a bond here. I have a bond here. Okay. Say I have one C double bond O here. Okay. Now this is the structure. Now I want to check out of these two H plus, which will be able to come out as easily, which will be able to come out as H plus more easily. Okay. So yeah. So basically, now what I have to do is again I have to remove the H plus ions and check for which O minus will give me. Say I'll first check for this, or I'll first check for that. Okay. So I'll put a O minus and a H. Okay. Now I have to check which proton is more acidic in the same compound. Okay. So now the only way I can do this is with the help of resonance. You will see whenever you have alternate double bonds and single bonds, you will know that resonance structures is going to happen. Right? Okay. Now if I check for this, what will be the first step? Okay, this doesn't have any resonance, right? Actually, wait, I'll just little tweak the structure. Or leave it like this, no issues. Okay, so now if I have a O minus here, right? Now this doesn't have any resonance structure. If I bring the bond here, nothing will happen after that. So if I write the resonance, nothing will happen. You will form a double bond O here. Nothing will happen after that. There is no resonance. Basically, this cannot undergo resonance. This O minus is not capable of undergoing resonance. Correct, right? But if I remove this one, if I put the O minus here, see how much will come. 1, 2, or basically I can directly put it here, and this bond can break. Okay, alternate. So this will make a double bond. If you're getting confused, draw the resonance structure. This will make a double bond. If this breaks, I'll get a negative charge. Again, make it here, and then this will form a negative charge here. That's how it goes. right? So the answer to this question is definitely this hydrogen is more acidic than this hydrogen. Okay, right? So like this, I'll be able to tell which is a better acid with the help of resonance structures. If you have resonance, obviously, not like for everything you will be able to use, right? But for if you have resonance, yes, like again. Now, what I wanted to tell you is, say in this case, you see some number of resonance structure. If there was some resonance possible for this also, right? Then what you have to do is the thing which has more number of resonance structures is more stable. Okay, the thing which has more number of resonance structures are more stable. Now, how many resonances will there? So one will be a negative charge formed here. That will be the first structure. The second would be this and this. Two resonance structures are possible for this, and for this none. So, anyways, if at all you had only one resonance structure possible for this, then you will tell that. Then also you'll tell that this is going to be more acidic. More and more resonance structure, more and more stable. Okay, right. Now say now if I go for say carbanions, carbocations stability, free radicals I will not be able to use it. Okay, I'll be able to use it for carbocations and carbanions. So, right. Okay. So if I have to do that, for example, okay, I'll take a smaller example. Okay, or something like this. Right. Now, what if at all you didn't know resonance, what will you see? Both are primary carbocations. Right. Now, obviously, with that, in the inductive effect will not help. Obviously, in this particular case, only inductive effect is possible. Now, this is going to donate electron, the amount of power is decreased, no doubt. Right. But if you look at here, right now, what can happen is since this has an empty orbital, this is sp2 hybridized, and this pi bond can directly come here, shift, just like how you do here, directly putting the double bond to the next carbon atom. Right. So I will be able to rewrite the resonance structure like this: CH2 plus. Now this carbon atom has lost the electron, so this will have a positive charge. Then I have CH double bond CH2. The positive is gone because the negative, the electrons would have come here. So this atom would have lost the positive charge, and this would have gained the positive charge. Right. Now these kind of carbocations are what are called as allyl carbocations, or this whenever you have C double bond C and a single bond C like this, right? This particular group is what is called as allyl group. Allyl carbocation, allyl halides, allyl alcohol, depending on what you have here. Say some X. If this can be a charge, then it is called allyl carbocation or carbanion or allyl radical. Right. Now, if this was an halide, then you'll call it as allyl halides. Okay. So you see both of them are primary, but obviously this is going to become more stable because of resonance. Okay. So again, if this was a carbanion also, right? Say if this was both of them were something like this is a carbanion. Again, this will be more stable. How? This bond will come here, this bond will break. Right. So how will you write the resonance structure now? CH2 minus CH double bond CH2. Right. So you see again for carbanions also, I will be able to check for stability settings. Okay. Right. So these are all the various applications of resonance. Right. You can do so many stuffs with this, but again, you have to practice a lot. Right. For you to master the resonance structures, you really have to practice. Okay, maybe now you will understand, but if you try it by yourself, right, then you might find it difficult. But for obviously you'll find it difficult for the first time, second time, third time, but after that you really are going to master this. Okay, fine. Any questions regarding resonance? Okay, fine.
No.
Yeah, okay, cool. Right, so that is about resonance. Right, now fine, one last thing and I'm going to complete the chapter. Okay. So if I have toluene, This is what is called as toluene, right? Benzene ring with CH3 is what is called as toluene. Okay. Now, this here also resonance structures are possible. Okay, but this is actually in your NCRT. They would have given the resonance structures, but what you understand is this carbon doesn't have any lone pair, right? And if at all you're going to say that it is going to behave as an electron withdrawing group, if you just make the bond, there is nothing else to break. Like if at all you had a C double bond, then you would have broken it, right? But here, how will you start the resonance structure? You tell me.
Sir, could you repeat the question?
Okay, the question is, how will you start the resonance structure? Where will you start the resonance structure from in this molecule? I'll give a clue. It is not only with respect to resonance. There is something else. So maybe this is too much of an ask. Maybe I'm asking you, but please understand, guys, hyperconjugation is possible here. Okay. Now, what I told you is I need to have an sp2 hybridized carbon, right? And next to that, I have an sp2 hybridized carbon. The next carbon atom should have a hydrogen atom in it. Correct, right? Don't you see that this carbon is sp2 hybridized because it is having a double bond, right? And the next carbon to that is definitely having a hydrogen. So this can involve in hyperconjugation. Okay, now if you want, you can check with this. If I had CH3, CH double bond CH2. Okay, right. Now, if at all I want to write the hyperconjugated structure for this, right? Now, how can I write this? Is again, you see, this is the carbon atom having sp2 hybridization. If I write it like this, now this is going to come out as H plus, and this bond can go here, and this can come here. Right? Now, how will I write the structure now? CH2 double bond CH, CH2 minus, and there is a H plus. Do you understand what I'm trying to do here? Right? I had this is capable of undergoing hyperconjugation. Now, the first step is only hyperconjugation. The next step is resonance. So this is a combination of resonance and hyperconjugation. Okay, there is a sp2 hybridized carbon. All the criteria which I told you for hyperconjugation is getting satisfied here, even though you don't have a carbocation or you don't have a free radical, right? But whatever the whatever the criteria rules I told you for hyperconjugation to happen, that is getting satisfied here, right? There is a sp2 hybridized carbon, and I have an alpha hydrogen attached to that. Right, so this will come out as H plus. This sigma bond will be put here, made a double bond. Obviously, this carbon cannot have 5 bonds, so this bond will break to make a negative charge. Obviously, H plus is going to be there. Right, now same thing I will be able to explain in terms of toluene also. Okay, fine. I'll give you maybe 1 or 2 minutes. Try to get the resonance structures out. First, go for hyperconjugation, right? Then do the resonance structures completely. I'll give you a minute time. Quick, go for it. Just like this. Now, in this case, you're only breaking one more bond, but if at all I had another double bond, then that will come and that bond will be broken. This exact same thing will happen. Okay, go for it.
Sir, and toluene, that's CH2, sir.
This is CH3 only.
CH3, okay.
Okay. I hope you would have drawn it, right? So anyways, let me write here and you check whether you got it right or not. Okay. So I write it like CH2H, right? Now what will be the first step? This H plus will come out and this bond is going to go here and this bond will break, right?
Yes, sir.
Okay, that's the first step. If you have gotten that right, everything else is going to be same. Just like an electron donating group, what you had for OH or NH2 or whatever it is, OR, whatever it is, exact same things will continue. Okay, so if you write it properly, I would have had a double bond CH2 with a positive, with a H plus, and this bond would have broken, and you had something like this, and all the other things will continue. You can again do this one will come here, this will come here, and then that will break. Eventually, it will go back to CH2 minus, and the H plus will again come back to form this one again. Okay, I don't think I have to explain the entire.
Sir, what would be the final structure, sir?
Final
structure.
Final structure would be this.
CH3, sir. At the end will be CH3.
Like you can write it as CH2 minus and then you can write it as H plus. Then you can combine them together to form CH3. Understood?
Okay, sir. Got it, sir.
Right? Okay. Yeah. So yes, that would have been the final structure. Okay. So yeah, that's about it, guys. That is about general organic chemistry. Okay. See where we started. We started with naming, IUPAC naming. Then we went on to see isomerism. So many types of isomerism, broadly classifying them as structural isomers and stereoisomers. Right? Actually, the better way of classifying them would be configurational isomerism and conformational isomerism. Right? Under configuration, again you have two. That is structural isomerism and stereoisomerism under configurational. Right? Again, structural can be of so many types: push chain, ring chain, functional, tautomerism, metamerism. Right? And under stereoisomerism, you have two: geometrical isomerism and optical isomerism. I told you optical isomerism you'll study in your 12th class, and geometrical isomerism we saw. Now, when I go for configurational isomerism, conformational isomerism, that is where I go for your Newman's formula, Newman's projection, Shawhorst projection, eclipse, staggered, all these things come under conformational isomerism. The conformational isomerism is always going to happen because of CC single bond rotations. We remember, right? Then we went on to see the flow chart of an organic reaction. I have something called as substrates that will be attacked by something called as reagents, and I'll form something called as intermediates. And these intermediates are unstable. They are eventually going to form products, right? So we studied about the substrates. That is, we studied about the IUPAC naming and their isomerisms. We studied thoroughly about the intermediates, right? So for intermediates, we went on to see how a bond fission happens, how bond breaking happens in organic chemistry. I told you there can be two ways, right? One is what is called as homolytic cleavage. The other one is heterolytic cleavage. When you have homolytic cleavage, that is wherever the electron came from, they're going to go back to their original parent atoms. You'll always end up with free radicals, right? Now, if you go for heterolytic cleavage, you can either have carbocations or carbanions depending on which element that carbon atom is attached. If the carbon is attached to a highly electronegative element, obviously the negative charge goes to the highly electronegative element, and the carbon atom would have had a positive charge. If it is going to be lesser electronegative, then you will see that carbon atom will form the negative charge. Okay, so three things are possible: free radicals, carbocations, and carbanions. There is some more: carbenes, nitrines, ketenes, so many other stuffs are there, but for our levels, you don't have to worry about it. Okay. Then we went on to see how to decide the stabilities. Okay, how do you decide the stabilities of carbocations, carbanions, free radicals? Right. For that, we went for inductive effect first. Inductive effect can be used only for charged species, only for carbocations and carbanions. So carbanion stability, primary is more stable than secondary. Secondary is more stable than tertiary. For carbocations and free radicals, we just now saw it is going to be ulta. Tertiary will be more stable than secondary, and secondary will be more stable than primary. Right. Then we went on to see how do you decide the acidic strengths, where I told you that you have to check for the stability of the conjugate base, right? So again, we saw so many stuffs. How do you decide that? With the inductive effect, we saw now use resonance also, right? For basic strength, we saw amines, right? Now tell me, what is the criteria for basic strength? Do you remember? What was the criteria for saying that, okay, this is more basic than this with respect to organic compounds? What is the criteria? What was the criteria for basis? Nobody remembers. Right. Okay, so this, because I don't remember, I'll just give you this thing, a quick recap, right? So remember, for basic strength is actually directly proportional to the availability of lone pair on that particular atom, and generally we only go for amines, right? So we know that Lewis bases are the one which will be able to donate lone pairs to other species, right? So obviously more and more is the availability of this lone pair, right? More and more will be the resonance, right? So then we took examples like this. If I had, say, I had CH, like I start with ammonia, CH3NH2, CH3NH, CH3, CH3N, CH3, CH3. This is my primary amine, secondary amine, and tertiary amine. This is ammonia, right? Now it's all about the availability of lone pair on this nitrogen, on all these nitrogens, right? Now what? Now tell me, which is the strongest base here? Which is the strongest base? Just look at that. Basic strength is directly proportional to the availability of lone pair. Where do you think the lone pair is
First
more?
structure, sir, the NH3CH3NH2.
Okay, any reasons for that?
More lone pair, sir.
That's what. How do you decide more lone pairs, more lone pair availability? Everything has one lone pair. So you have to use your inductive effects. Now, what do you understand? Here I have one electron donating group, which is going to increase the availability of lone pair on this nitrogen. Now here I have two electron donating groups going to increase the electron availability on this nitrogen. Now in this case, I have three electron donating groups increasing the availability of lone pair on the nitrogen, and ammonia has nothing. It is just having hydrogen, right? So obviously the order of basic strength for the amines and ammonia would be tertiary, greater than secondary, greater than primary, and least would be for ammonia. Yes, everybody understood why is it like this? More and more availability means I should have electron donating groups present near the nitrogen, which is having the lone pair. Then it is going to increase the availability of lone pair, thereby increasing the basic strength. Yes, understood?
Yes, sir.
Okay, good. Right. Now, actually, I forgot one thing. Now, say I compare these three things. We already know what is the order. And if I have aniline, this is called as aniline, NH2, benzene ring with NH2 is what is called as aniline. Okay, now tell me, when I compare, say, tertiary amine with aniline, tell me which is more basic. I have tertiary amine, or any of this you take tertiary amine. Okay, we'll take tertiary amine, and I compare with aniline. This is also amine, right? Benzene ring with an amine. This is also okay. You can even say that this is a primary amine. This is a primary amine, right? Oh, it is attached to only one other carbon atom. It is attached to one other carbon atom. Here also one carbon atom, one nitrogen atom. Okay, so if I compare primary amine with this primary amine, this is also a primary amine. Tell me which is a better base. Okay, we'll take a vote. How many of you say primary amine or this one? Aliphatic primary amine is more basic. How many of you say that? It's just a guess game. How many of you think that this one is more basic than this? Okay, fine. So how many of you think that this is going to be more basic? What is this?
1 minute, sir. I think.
Yeah.
Don't know.
No, it's okay. It can be a guess, right? It doesn't matter whether you're correct or wrong. What do you think? How many of you say that this is going to be more basic? We'll take a vote. How many of you say this? The aliphatic primary amine is more basic, sir. How many of you say that? Nobody says. Then I can say that everybody says that the aromatic amine is more basic. Can I take it that way?
Yes, sir.
Okay, fine. Now, I don't know how you think about this, but I want to know, why do you think like that? See, it doesn't matter whether you're correct or wrong. I just want to know how you think. Tell me, why do you think that this is going to be more basic? Now, I told you what is the criteria for basic strength, more and more availability of lone pair. Please remember that. Okay, now tell me, why do you think that here for this amine, there is more availability of lone pair? Only in that point.
There's a double bond, no, sir. Due to that.
Okay, so where's the double bond? This double bond you're talking?
Yes, sir. Yes, sir. That double bond.
Okay, because of the double bond, what is going to happen?
So if that C donates electrons to NH2, sir, the double bond will.
No.
take
Wait. See, you are telling that this double bond will donate to this nitrogen. It's what that would do?
Somewhat in that sense, sir.
Okay, now look at this. If I take ammonia, for example, that's the derivative of this. I don't have the benzene ring, I have this one. Okay, I have a lone pair. Right. So now tell me, if I give one more any other bond, will it take? Do I have, what is the hybridization of this? Can you tell me? Okay, what is the hybridization of ammonia? What is the hybridization of ammonia? I mean, nitrogen and ammonia. What is the hybridization?
sp3, sir.
sp3, like 3 bonding atoms and 1 lone pair. sp3, right? Do I have any empty orbital on nitrogen to accept it?
No, sir.
No, that means that is not possible. But obviously, what you have seen in the resonance structure, I told you, if at all there is some species which is having lone pair, the resonance structure starts with the lone pair. So obviously, you see that the lone pair will be donated and this structure goes on. Right. So because of resonance in this, what is happening to the availability of lone pair on nitrogen?
Decreases, sir.
Absolutely. Right. So remember, whenever you have aniline or any derivative of aniline, that is actually going to be less basic even than ammonia. Because at least in ammonia, I don't have any electron donating group to increase the availability of lone pair, but there is nothing to decrease it also. Right. But in alanine, you see that the lone pair is not available on nitrogen. It is actually involving in resonance. Right. So thereby the availability of lone pair on nitrogen aniline is very much decreased, decreasing the basic strength also. Okay. Now if at all I give one more example, say if I had something like this. Okay. Now if I compare it with again the primary amine, this is also a primary amine. Right. Now again, what do you see? This lone pair is actually not on nitrogen. This is involving in resonance. Right. But if I compare this with this, what do you think is more stable? The aliphatic one or this one? Say if I mark it as 1 and 2, tell me which is more basic.
1, sir.
Definitely. Right? Because here there are more number of resonance structure, but here just only one resonance structure. Not so much will happen. So definitely one will be more basic than two. Okay. So comparing with any kind of amine, aniline is actually going to be very, very, very less basic because it is the lone pair on nitrogen is involved in extensive resonance. Okay. So hope you all understand why aniline is going to be least basic. If someone asks you what is the reason, tell them that the lone pair is not available on nitrogen because it is involved in resonance with the benzene ring. That's how you must answer the question. Okay, so what is the time?
Yes, sir.
Yeah, so it's 7 o'clock, 6:59. We'll take a break. Okay, we'll meet by 7:10. Okay, you don't have to go out. Okay, please don't go out. Please mute yourself and then go, and then you can come and join. Okay, go have your coffee or whatever you want to do. Just come back in 10 minutes. I'll be here by
Okay,
7:10.
sir.
Okay, I'll switch off my video and I'll mute myself, but I'll come back by 7:10. Okay.
Okay.
Yeah. Off your back. Everyone, moment. Wait. Okay, shall we start? Are you guys there?
Yes, sir.
Yes, sir.
Okay, good. Right. So we have completed a big chapter. Right. So now we continue with organic, right? And guys, for your S block and P block, so you have group 1, group 2, group 13, and group 14. Correct? Am I right? Yes? No? Did you study about, you have studied about lithium family, you have studied about beryllium family, boron family, and carbon family. Is that what you have in your 11th?
Which chapter, sir?
S and P block. S block elements, I'm not sure. Is it called S block elements?
Yes, sir. It's S block.
Ah, okay. S block, you have only group 1 and group 2. That's it, or you have group 13 and 14 also?
1 minute, sir. I check.
Yeah.
Even only till group 2, sir. Till beryllium and magnesium calcium.
Okay, okay. So only you have group 1 and group 2, right? So for that, what will we do is I'll conduct a quiz in the sense that you will prepare, say we'll take one day group 1, the next day group 2 will complete it. Okay. So when I say tomorrow, not tomorrow, maybe when I finish this chapter, we'll be going for group 1, right? So I'll tell maybe 1 or 2 days before. So you will prepare, you will study entirely the group 1 alone and come, right? And I will conduct a quiz, right? And since you have very less number of people, you have around only 7-8 people. I don't think I want to make it into groups, right? I don't think that will be a good criteria, right? So everybody will be in individual teams. Okay, right? And whomever is present, good for you. Whomever is not present, losses for you, right? So you will prepare that and come, and I'll ask you questions, okay, and you will be answering it. So 1 day for group 1, 1 day for group 2. Group 1 means not the groups of you, the periodic table group 1, group 2, and everybody will be in individual teams. Okay, so prepare nicely and come. I'll tell you at least 2-3 days before. Then we are going to start that. Right after we complete this chapter, we'll be starting. I think this will, compared to GOC, this is going to be a very small chapter, right? Maybe I'll be completing in 1 or 2 classes. So you can right away start preparing. Group 1, you start preparing. Is it okay? Right? Fine. So that I want to tell you. Now we'll start. We will start with hydrocarbons. Right? Now, this is the first chapter you will be studying organic reactions, right? Till now you just saw only certain things about organic molecules, but this is the first time that you will be studying about their physical properties, their chemical properties, and all these stuff. You'll first time go for organic reactions, right? And please understand, I am not going to teach you how they are given in your textbooks. Okay, so in your textbooks, they would have just given the reaction. They would have given the reactants. They would have given the products. That's it. Now, but that will really not make sense if you like. If at all, I can do that. But again, what you have to do is you have to mug it up, right? So what we will do is we will see the inside things, right? So I told you that flowchart, hope you remember, right? We said that I'm going to have something called as substrates that will be attacked by something called as reagents. I have something called as intermediates, and then the products, right? So that is what is called as mechanism of the reaction, right? What is inside happening? You don't see just the reactants and products. You are going to go inside the reaction. You are going to see step by step what exactly is going to happen, right? So you might not be using it for your exams. Nobody is going to ask you that in the exams with respect to your schools, but with respect to your knowledge, that is how you should learn organic chemistry. That is the only way you should read organic chemistry. Mugging up the reactions is really not. At least me, I'm not going to teach you like that. Okay, so if at all you feel that this is going to be too much information, like I would say, bear with it, because that is how you should learn it, and that is how you will be able to appreciate the reactions. Okay, fine. So we will start now. Hydrocarbons can be classified into two basic types, right? Now hydrocarbons, that means I am going to see organic reactions. I am going to study about organic molecules which are going to have only hydrogen and carbon. That's what the name says, hydrocarbons, right? Okay, now this hydrocarbons can be classified into two types. One are what are called as aliphatic hydrocarbons, and I have something called as alicyclic hydrocarbons. Okay, right? Now in this aliphatic hydrocarbons, again I can have two things. One is what is called as saturated hydrocarbons and unsaturated hydrocarbons, that we already know, right? Saturated hydrocarbons are going to have only single bond Cs. Unsaturated is going to have double bond Cs or C triple bond Cs. What do you mean by aliphatic? They are straight chain compounds. They don't have any ring in them. They are linear structures, straight chain molecules. Alkenes, propane, butane, butene, all these things comes under aliphatic. Right. Now, when I go for alicyclic, you have actually two types, right? This is not only for hydrocarbon people. This will hold good for any of the functional group, right? If at all it was a hydrocarbon, certain things will not match. Say, if I got to go for any other functional group, you have something called as homocyclic molecules, and you have something called as heterocyclic molecules. Homocyclic molecules, example is okay, fine. Homocyclic molecules means in the obviously alicyclic structure, alicyclic molecules are going to be cyclic structures: cyclopropane, cyclobutane, cyclohexane, cyclohexene, all these things. Right now, what do you mean by homocyclic? Means in the ring, right? In all the members of the ring are going to be carbon atoms, in the sense that whatever you know till now, right? Benzene, cyclopropane, cyclopentane, all these things that comes under homocyclic. Heterocyclic means in the ring, in the cyclic structure, one of the carbon atom or more than one carbon atom is replaced with another element. For example, you have something called as pyridine. Something like this. Now, what you see here in this structure is that there is, if at all this was a carbon atom, then it would have been a normal homocyclic compound. But other than a carbon atom, you have a nitrogen atom here. Those things comes under heterocyclic compounds, but we really don't have to study. Even if you go to 12th class, even if you can attend for JEE Mains, JEE Advanced, you really will not study about all these things. But again, just know it, right? Homocyclic means all the vertex are carbon atoms. Heterocyclic means one of them or two of them are going to be different elements. Okay, fine. Now under homocyclic, right, you have two things. One is what is called as aromatic molecules, and another one is what is called as non-aromatic molecules. Right now, you don't have to worry about it. Aromatics are benzene structures. Right, benzene is an aromatic compound. Okay, benzene is an aromatic compound. Right, again, there are certain rules. There's something called as Huckel's rule to determine whether a particular compound is aromatic or not. But I don't think you have it in your syllabus. Do you have Huckel's rule? Huckel. Have you ever heard of this? Do you have it in your syllabus? Huckel's rule.
What is it about, sir?
It is about deciding whether the compound is aromatic or not. Do you have that? I don't think so. Right. Anyways, don't worry about it. Okay, you don't have there's no questions going to come from this. So aromatic means benzene. For now, that is enough. That is more than enough. All benzene structures. Okay, fine. Now, when I go for non-aromatic molecules are non-benzene compounds. Now, like when you have non-benzene cyclic structures, cyclopropane, cyclopentane, cyclohexane, any other thing which is not benzene, any other cyclic structure which is not benzene comes under non-aromatic structure. Actually, there is something called as anti-aromatic also, but again, too much information for you. Just remember that it's going to be alicyclic, homocyclic, heterocyclic. Only homocyclic we have, right? Under that we have aromatic and non-aromatic. Aromatic means benzene, non-aromatic means non-benzene compounds. Any other cyclic structure. Okay, right? So these are the different classifications of hydrocarbons, right? Okay, fine. So this is the simple. This is just simple. Right? We'll move on. Okay, right. Now, we are going to study about alkanes, alkenes, alkynes, and benzene compounds. That's it, right? We will not generally study about your alicyclic non-aromatic compounds, but again, they're going to behave exactly as the other structures. Now, aliphatic hydrocarbons, how they behave, the same way only alicyclic also will behave, but benzene will be different, right? Aromatic compounds will be different. Okay. Anyways, right. So now first we'll start with the physical properties. Okay, physical properties of hydrocarbons. Just give me a moment. sorry guys, are you guys there? Okay, I'm sorry guys, I had to attend a call. It was a very important call I had to take. Okay, I'm sorry. Fine, we'll start. So we are going to see physical properties of hydrocarbons. Okay, now remember, not only in this case, you will be studying about, say, when you go for 12th class, right? In this 11th class, what you saw is very less of organic and more of physical chemistry. Physical chemistry in the sense, the problematic, starting with gaseous state, stoichiometry, thermodynamics, equilibrium, all these things comes under physical chemistry, right? Now in organic, now if you go to 12th class, right, you will see less of physical chemistry and more of organic chemistry. Now you are introducing your hydrocarbons, correct? Now you will take, there'll be a separate chapter for alkyl halides, there'll be a separate chapter for alcohols, there'll be separate chapter for acids, there'll be separate chapter for aldehydes, ketones. So like this, like different functional group you'll study as a different chapter. Okay, right. So anyways, when we go for that, we'll understand. But anyways, for all these functional groups, including hydrocarbons, when I say physical properties, you will speak about three things. Okay, the first one is, I will say through two things only. One is boiling point and melting point. Okay, now second thing is about the solubility. Okay, solubility in water or solubility in some other solvents. Okay, so now what am I going to do is that if I give you 2 or 3 hydrocarbons, right? Now, how will you decide which is going to have more boiling point or melting point, or say which is going to have more solubility, right? So all the, now solubility will not be able to decide like that, but still, like whether I'll be able to tell whether that particular hydrocarbon is soluble or not in water, that I'll be able to tell. Okay, fine. So first, speaking about boiling points or melting points, boiling points, for you to decide, for you to arrange hydrocarbons in terms of boiling points and melting points, you have two criteria, right? One is the molecular mass. We know how to calculate the molecular mass, correct? And second one is about the branching. Hope you know what is branching. I can have a straight chain compound, the same molecular formula, I can write a branch structure. I can put a CH3 as a branch, C2H5 as a branch, so on and so forth. Right? Okay. Now, based on these two, how will you decide? Right? Now, please understand, we are talking about the van der Waals forces. Okay. We hope you remember when we saw chemical bonding. Hope you remember we saw van der Waals forces. Van der Waals force is a universal force. Right? So hope you understand, like if you can remember that van der Waals forces are going to be more and more if I have more and more number of electrons present. Right? Because I told you it is because of some temporary polarity and stuff. But if you don't remember, do not worry about it. Okay. Now please understand, boiling point or melting point is directly proportional to the molecular mass of the compound. Right? Say for example, if I compare methane with ethane, right? So obviously I know ethane is going to have more molecular mass. So ethane will have more boiling point or melting point than your CH4. Same if you have propane, propane will have more boiling point or melting point than ethane. Okay, so that is the criteria. More and more molecular mass, more and more boiling point or melting point. Right. Now, next thing, when I go for branching, now here it is going to be inversely related. It is going to be inversely related, right? So that means more and more branching, less and less would be the boiling point. Okay, now how do I put it? If I have to take an example, this is say for example, if I take normal butane, CH3, CH2, CH2, CH3, right? And if I compare it with the isomer of this is my chain isomer, is it not? Now this has no branching, this has one branching. Correct, right? So now I told you more and more branching, less and less will be the boiling point. Now this has more branching, this has less branching. So this is going to have more boiling point than this particular compound. Okay, so molecular mass directly proportional, branching inversely proportional to the boiling point of the particular species. Okay, right. Now that's about boiling point or melting point. Only two criteria. Actually, there is one more criteria. One more criteria would be hydrogen bonding. But I know in hydrocarbons, there is no way that I can have hydrogen bonding, right? For hydrogen bonding, hope you remember, I should have something called as hydrogen donor. I should have something called as hydrogen acceptor. Then if it is there, then the hydrogen bonding is possible. But here, we have nothing. So hydrogen bonding is not even a criteria here. Okay, fine. Now, going to solubility, right? Hope you remember one thing when I spoke about hydrogen bonding or anything about related to solubility. If I have spoken, and if you remember that, I would have given you this particular statement. Do you remember? Like dissolves like. Do you remember the statement, people? No? Okay, right. So let me explain you what do you mean by this, right? Like dissolves like means if I have one kind of substance, one type of substance, one type of solute, that particular type of solute will dissolve only in that particular type of solvent. Again, I repeat, if I have one type of solute, that particular solute will dissolve only in that particular type of solvent. Right. Okay. Now, what are the types? Only two types: polar, non-polar, and we know how to decide whether it's going to be polar or non-polar. Right. Polar molecules will have high difference in electronegativity between the bonding atoms. Non-polar molecules are not going to have any electronegativity difference, or I would say very less electronegativity difference between the bonding atoms. So, what do you mean by that is if I have a polar solute, that will dissolve only in a polar solvent. If I have a non-polar solute, that will dissolve only in a non-polar solvent, right? Polar solute dissolve in polar solvent, non-polar solutes dissolve in non-polar solvent. That is what you mean by this particular statement, like dissolves like. Okay, now, based on your observations, based on your understanding, tell me whether hydrocarbons can be considered polar or non-polar. Hydrocarbons can be considered polar or non-polar. What is
Can
your
be
take?
polar, right, sir?
Okay, so what you understand is here I'm going to have either CC bond or I'm going to have CH bond. These two are the only possibilities. CC bond definitely not polar, right? Now CH bond, you might say that carbon is more electronegative and
Yes,
hydrogen
sir.
is electronegative, but again, the electronegativity difference is not so much. Very, very little electronegativity difference will be there. Okay, so remember, hydrocarbons are non-polar molecules, or they are not, they are very, very less polar, very, very less polar molecules, right? Now, so now, keeping this in mind, tell me whether these hydrocarbons can be soluble in water or not. Remember this statement and remember that they are non-polar, and tell me whether hydrocarbons can be dissolved in water or not. Water is what kind of solvent? Water is what kind of solvent? Polar or non-polar solvent?
It doesn't dissolve, I think, because water is polar.
Correct. Right. So you see there is a OH bond. Obviously, I'll have del positive here, del negative here because I have high electronegativity difference. Oxygen is very, very highly electronegative, and hydrogen is actually electropositive in nature. Right. So water being a polar solvent will not be able to dissolve hydrocarbons, which are non-polar in nature. Right. So what you have to understand about solubility of hydrocarbons is that they are insoluble in water. Right. They are insoluble in water, but they are soluble in organic solvents. Right. Now, if you ask me, sir, what are organic solvents? Organic solvents, I can give you examples like I have benzene is a good solvent. Benzene actually is a liquid. Benzene itself is a hydrocarbon, but still, it is a non-polar solvent. So it will be able to dissolve other hydrocarbons. There is something called as DMSO, DMFO. DMSO is dimethyl sulfonyl oxide, but again, you don't have to worry about it. So these are all the different non-polar organic solvents which will be able to dissolve the hydrocarbons. But what you have to understand is no hydrocarbon literally will be able to dissolve in water because hydrocarbons are non-polar, but water is polar. So because of that, they are insoluble in water. Is that okay? Right. So that is about the physical properties. Boiling point, melting point, we saw what is the criteria, molecular mass and branching, right? And for solubility, you have to remember that it is going to be like dissolves like, and you have to understand that they are insoluble in water. Okay. So that is about the physical properties of alkanes. Not alkanes, sorry, hydrocarbons. Right. Okay. Right. Next thing. Right. So next thing is, how do you prepare these compounds? Preparation. Okay. How do you prepare these compounds? Okay. Fine. Preparation, we have to see for alkanes and alkanes separately. Right. For alkanes, generally we don't have any set of preparation because mostly they'll be naturally available. Right. First, we're talking about alkanes. Right. So alkanes generally are mostly naturally available. Right. But they're mostly naturally available. But still, there are some synthetic methods by which you'll be able to prepare, but not all hydrocarbons. Okay. Say, for example, if you have carbon monoxide and if you react with H2, right? Oh, I'm not sure. Carbon monoxide with, 1 second, guys. Just give me a moment. Oh, okay, not CO, it is carbon. Carbon in the form of graphite. Okay, carbon in the form of graphite, and if you put hydrogen at 100 degrees Celsius, you will be ending up with CH4. Or say if you just increase the temperature, say to 1200 degrees Celsius, you will be ending up with ethane, something like this. But again, what you have to remember is carbon plus hydrogen gives me hydrocarbons. That's what you have to remember. Temperature is not much, right? And then what you can understand is from alkenes, I will be able to prepare alkanes. Right. So when you have, this is the first method. This is, I would say, in this mostly are naturally available. This is the first method. Second method is from alkenes or alkynes. Right. From alkenes or alkynes. Say, for example, if you have C double bond C, right? Now, if you add hydrogen to this, right? But again, you cannot just directly add hydrogen because please understand that this H bond is very strong bond. Okay, one of the strongest bonds in chemistry is HH bond, right? So what you have to understand is this bond need to be broken, and this pi bond also need to be broken, and these two hydrogen atoms will add here and add here, right? So you will see that I'm going to have, see this, when I just empty, that can be anything, right? See double bond C with two other bonds. Okay, so these two hydrogen atoms are going to add here, but you cannot directly do it. You need to use a catalyst. Okay, now that catalyst can either be nickel, or it can be palladium, or it can be platinum. Okay, any metal surface will hold good for me, right? Okay,
So I have a doubt.
Yeah,
this is called hydrogenation, sir.
Exactly, this is called hydrogenation reaction. Okay, I don't have space right here. Okay, this is called hydrogenation reaction.
Both are hydrogenation, sir.
Which is both the hydrogenations?
One first method as well as second method.
No. This is just combination reaction. Combination of hydrogen and oxygen, hydrogen and carbon. This is combination, normal combination reaction. This is hydrogenation reaction.
Okay, sir, understood.
Okay, right. Next thing. Okay, that I think this is the only thing you will have in your syllabus. Again, same thing if I go for any, where is my duster? Okay, so anything, if you go for alkenes, right? So alkenes, again, they will have C triple bond Cs, right? Now, again, if I put H2 in the presence of nickel or H2 in the presence of palladium or platinum, again, you have to add 2 moles of H2 in this case, because you need to make you need to break 2 pi bonds and add 2 moles of hydrogen molecules. So again, you will be ending up with CH2, CH2, and the other group, whatever was left here. Okay, so again, that is also hydrogenation of T. Right, now, how this reaction happens is the question. Right, now I told you that this bond, HH bond, is one of the strongest bonds in chemistry. Right, so I told you that this nickel or palladium or platinum is going to help me. Right, now how is it going to help? Let me tell you. Now remember, if it was ethene, I'll be ending up with ethane. Right, okay, anyways, if this was ethine, and I'll be ending up with ethane again. Right, okay, so now what you have to understand is, guys, both are gases. This is a gas. Hydrogen is also a gas. H2 is also a gas. Right, now this nickel or palladium or platinum is going to provide me a surface. Right, and there is going to be a phenomena, right? There's going to be a physical phenomena called as adsorption. Okay, ADSORPTION, adsorption. Okay, now you might have heard about absorption, AB, B for bat, right? Like, okay, now this is also kind of absorption only, but little different. Okay, let me tell you the difference. I take a sponge, right? I dip it in water, or I dip it in any kind of liquid. What will you see? The water molecules will be on the surface of the sponge, will be inside the sponge. Everywhere in the sponge, you will see water molecules, or whatever the liquid you would have taken. Right, now what I do is that I take a chalk piece. Their teachers use for teaching, chalk piece. Right, I dip it in water. I dip it in a tumbler of water. Okay, now what will you see? You will see that the water molecule or the water will be on the surface of the chalk. Right, but if you break the chalk and see, there will be no water inside. Do you agree with my point?
Yes, sir.
Right, again I repeat, you have a chalk, you dip it in a liquid, or say for example water, you will see that the water molecules will be on the surface, no doubt about it. Right, but if you break the chalk and see, you will see that there is no water molecule inside. That is what is called as adsorption. Adsorption is absorption, but only on the surface. As simple as that. Adsorption is absorption. AD is AB, but only on the surface. Absorption happening only on the surface is what is called as adsorption. Okay, now there'll be a separate chapter for adsorption in your 12th class. Surface chemistry is the chapter. That time we'll see what, like, there's so many inside details I can give you about this. Okay, so for most of the catalysts, and you'll see so many catalysts, right? Most of the catalysts are actually going to provide the surface for adsorption to happen. Okay, now what is going to happen is you have two gases, ethene and H2. Right, so this ethene and H2 will get adsorbed on the nickel surface or the palladium surface or the platinum surface. Even hydrogen atom, hydrogen gas will also get adsorbed on this surface. Okay, now there'll be some kind of temporary interaction between the ethene molecule and the surface, and there'll be some temporary interaction between the hydrogen molecule and the surface. Okay, now because of this, what is going to happen is, now because of this temporary interaction, this HH bond gets weakened. Right, this HH bond gets weakened. Same way, this I have, because of the temporary interaction here, this pi bond also gets weakened. Right, now since I have weakened the bond, then they are in very close proximities, they are very near to each other. The chemical reaction will happen, and then you will end up with this molecule, ethane molecule. Okay, so this is the mechanism. This is what is called as the mechanism of the reaction. Okay, so this is how, by hydrogenation, you will be able to prepare alkanes from alkenes and alkynes. Is it okay? Right, these only two methods of preparation. One from carbon plus hydrogen, carbon graphite plus hydrogen gives me hydrocarbons, or by hydrogenation, you will be from alkenes and alkynes, you will be able to prepare alkanes. alkanes. Okay, right? Fine. So that is about alkanes preparation. Now we'll move on to alkenes preparation. How am I going to prepare alkenes? We'll see. Right. Okay. So second is alkenes. And alkenes is very important with respect to preparation because you'll have so many reactions coming. Okay, now first one, right? I will be able to do it from alkenes. Now, how you prepared from alkynes by hydrogenation, right? From alkynes by hydrogenation. Now, in this case, you saw I added 2 moles of H2, right? Now I'll add only 1 mole of H2 to form alkenes, right? Now there is by direct hydrogenation in this itself. Okay, fine. So now if I have C triple bond C, say if I have CH triple bond CH, and if I go for 1 molecule of this, okay, now I'll be ending up with CH2 double bond CH2, right? Now if this was something like this, CH3 C triple bond C CH3, something like this if I had, right? Now if I go for H2 bar nickel, right? Now what you will understand from the previous thing is that, say for example, if this is my ethyne molecule or whatever the alkyne molecule, if I have it like this, the hydrogen atom, the hydrogen molecule will add up like this in the same side, from the same side, because they're going to be on the same surface, right? The alkyne molecule and the hydrogen molecule will act like both the hydrogen atom will add from the same side. It's not like one hydrogen atom will come from here, the other hydrogen atom will come from up, from top. No, it is not like that. Okay, so please keep this in mind. If that is the case, you will be ending up with a compound like this. I'm writing the product here. You will be ending up with C double bond C, obviously, right? Now you would have had 2 hydrogens which is going to come from the same side. Say 1 hydrogen down, another hydrogen down, or 1 hydrogen the top, another hydrogen also should be the top. Okay, now what is remaining? CH3 is remaining, right? So CH3 and CH3. Now tell me, what is special about this?
This is called cis isomer, I think.
Exactly, right? So whenever you go for hydrogenation reaction like this with an alkene, you will always end up with cis alkenes. That is the point you need to remember. You'll always end up only with cis alkenes, right? Now you can ask me,
for every alkyne, sir. For every alkane, if you do
any alkane, if you go for hydrogenation, this reaction, right? But I can do the hydrogenation a little different way. Now but I can't call it as hydrogenation. But anyways, now from alkyne, I will be able to prepare a trans alkene also, but not by this reaction, by some other reaction. I'll tell you how it is that reaction. Right? So when you have an alkyne, when you go for hydrogenation reaction, H2 bar nickel is what I'm talking about, you'll always end up with cis alkynes, right? Okay, now there is one more thing also. When you have, say, this CH3 C triple bond CCH3, right? Now if you go for sodium in liquid ammonia, right? Sodium in liquid ammonia, right? What will happen is you will get the trans product, or okay, you will end up with the trans product. Now you can ask me, sir, why is it happening like this? Okay, now the reaction mechanism is little complex. If I explain you, maybe it will blow your mind. But what you have to understand is, somehow from this I am going to get H plus and H minus. Okay, somehow you are going to get H plus and H minus. Okay, right? Now what is going to happen? So first, this H minus, or generally it will be H plus with a attack. I'll tell you what exactly is this. So first, the H plus, assume that is going to come from the downside, right? And you have added 1 hydrogen, right? Now due to, now you see already there is a hydrogen at the bottom, right? So if the second hydrogen in the form of H minus also comes, right, it will face repulsions, right? So remember, organic reactions will always take place in a path which is easier for them, and easier in the sense wherever I have lesser energy to spend on. Okay. Now, obviously, if at all this H minus also is going to come from the bottom, it will suffer repulsion. So we have to spend more energy, and we have to the reaction will require more energy. So, but there is another way, right? If this H plus comes from the bottom, and if this H minus goes to the top, then I will spend lesser energy, right? So that is the reason why you will always end up in alkene if you're gonna go for sodium in liquid ammonia. Okay, so normal hydrogenation reaction always successes alkene, but if you have an alkyne and if you react with sodium in liquid ammonia, you will always end up with trans-alkene. Okay, this you will remember, right? Fine, that is one way of preparation. Now, there are two ways. This is actually, you can call it a second reaction. You can call it a second reaction. Alkynes with sodium and liquid ammonia, then alkynes with hydrogen bar H2 bar nickel or H2 bar palladium. Two reactions done. Okay, right? Fine. If you like, just remember that I'm going to have H plus and H minus coming from opposite sides. That's it. That's why you end up with a trans-alkene. Okay. Now, what is the time? Okay, we have 20 more minutes. Cool. So next, what are the other ways of preparing? Okay. Okay. The third way of preparing is by elimination reactions. Right? By elimination reactions. Very simple. Let me give you the reaction first, and I'll give you the mechanism, and then we'll see some examples. Okay. Say if I had some C which is having a H, and there is next C which is having an Lg. Lg represents a leaving group. Lg represents a leaving group. It is going to leave from the compound. That's what you can understand. Say this can be highlighted. It can go out as H, Cl minus, Br minus, or say if I have a OH, it can go out as H2O. Something, some leaving group is there. For now, just remember that Lg means leaving group. Okay, right. Now, if it undergoes elimination, I just write as E means elimination. What will happen is this H plus will come out, and this leaving group will leave as Lg minus. H plus, Lg minus. Say for example, H plus Cl minus will form HCl. Right. So now what will happen? This bond, this bond will go here, this bond will go here. So you'll always end up with alkyne plus H plus the leaving group. Okay, this is what is called as your elimination reaction. Okay, right.
Could you
now
repeat?
Yeah, sure. So so I have a normal alkane molecule. This is a saturated molecule with some leaving group. I'll tell you leaving group how they're going to be. So I'm going to have some leaving group. Right now, this leaving group, so H plus and the leaving group along with the negative charge leaves. So what will happen? One bond is missing for this carbon, one bond is missing for this carbon. Now they both will come together to make a double bond. So you'll end up with an alkene. Okay, yes, so alkene, H plus and Lg minus. Lg minus is leaving group with a negative charge is what you're going to have. Okay, I hope everybody understood what exactly is happening here. Right now, I will not be able to. There are two ways by which this is possible. Okay, there are two ways by which this is possible. Right, elimination reactions is possible in two ways. So what are the ways? I'll tell you. First one is what is called as your E1 elimination, or it's called as E1 mechanism. First we'll see E2 mechanism. Right, so I have something called as E2 mechanism, and I have something called as E1 mechanism. Okay, for you to understand E is elimination, that is okay. What this 2 represents, let me tell you. Okay, you need to have actually better knowledge for that. You need to know there's a separate chapter called as chemical kinetics, which you'll be studying in your 12th class. Anyways, I'll just try to explain you what exactly is this. right? So when I say E2, I mean 2 represents it is going to be a bimolecular reaction, right? It is going to be called as a bimolecular reaction. Okay, now what is going to happen here? Let me tell you, right? Say I have a hydrogen and I have a leaving group. Okay, right? Now what is going to happen is, obviously now for removing H plus, I need to have a base, correct? For removing H plus, I need to have a base. Okay, now what is going to happen is this base is going to take up the H plus, simultaneously this also leaves. Let me tell you again, right? So I have hydrogen, I have leaving. So basically you are going to break 2 bonds, the CH bond and the C leaving group bond. 2 bonds you are going to break, right? And both these bonds will break simultaneously at a time. Both of them will break. Okay, base will abstract the proton and the leaving group leaves simultaneously. Okay, so you will end up with an ion. Very simple. Okay, this is what is called as E2 mechanism. In E2 mechanism, 2 bonds are broken, and even also 2 bonds are broken. But in E2, both the bonds are broken simultaneously at the same time. Both the bonds are broken. Okay, right. Now I have to tell you what do you mean by this two. Okay, so guys, we spoke about rate loss. If you can remember equilibrium. If you remember equilibrium, there was something called as law of mass action. Do you remember? At least do you remember the name? Law of mass action. Do you remember? Okay, fine. Or if I have to put it in a nutshell, right? So you see here, there are 2 molecules reacting. One is the whatever the compound I have, the other one is the base. Okay, now if you see that the rate of the reaction, the rate of this reaction depends on the concentration of this, the whatever the substrate and the base, right? The rate is directly proportional to the substrate as well as it is directly proportional to the base. So this is what is called as a bimolecular reaction. That means the rate of the reaction is affected by change in concentration of this as well as change in concentration. Bimolecular. 2 molecules decide the rate of the reaction. Okay, that is what is called as your bimolecular reactions. 2 molecules affecting the rate of the reaction. Right. Now, when I go for E1, obviously you'll understand that I'm going to call it as a unimolecular reaction. That means either this or this will be capable of affecting the rate of the reaction. The other one, even if you change the concentration, has no role to play in deciding the rate of the reaction and how fast or how slow the reaction happens. Only one of them will decide. But in this case, both the concentration will have a role to play in deciding how fast or how slow this particular reaction is going to happen. Okay, now this is what is, so what are the things you have to remember? You have to remember that the 2 bonds broken, both the bonds are broken simultaneously. Second thing, the rate of the reaction depends on the concentration of both this as well as the base. 2 things you have to remember. And next thing is, right, now okay, fine. So this is about E1 mechanism, E2 mechanism, right? Now, when I go for E1 mechanism, okay, when I go for E1 mechanism, say I'll take the same thing. I have a H, I have a leaving group. Okay, now now remember, this is a single step reaction, single step process, because you see at a time both the bonds are broken. Right. Now remember, E1 mechanism is going to be a 2-step process. Right? E1 mechanism is going to be a 2-step process. And this one represents that it is going to be a unimolecular reaction. Unimolecular means the rate of the reaction depends on only one of the compound. Even though I have 2 reactants, only one of the reactant will decide the rate. Okay, and obviously that is going to be this one, the substrate. The substrate only has some role to play with respect to the rate. What is the other one? The base has no role to play. It is not going to affect the rate of the reaction. Okay, so anyways, now I told you that it is going to be a two-step process. Right, now two-step process means the first step is the removal of the leaving group. The leaving group first leaves, taking the negative charge along with it. Right, so now what will form? You will see that this H is still remaining and this is gone. Now can I say the carbon atom will have a positive charge because the leaving group would have taken the electron along with this? Right, so you see the intermediate, this is the intermediate, carbocation is the intermediate here. Okay, here the intermediate is nothing, like both the bonds are broken and simultaneously you have, but here I have one intermediate, that is my carbocation. Right, now what will be the next step? Obviously now I have to remove the H plus, and if I remove the H plus, then eventually I will be able to easily form the bond, that is double bond. Right, now what is going to happen is I'm going to put the base, which is going to abstract this H plus. So basically what is going to happen? This bond is going to go here and this comes out as H plus, minus H plus. So what is remaining? I will have C double bond C. So the first step is removal of leaving group to form the carbocation. Second step is removal of H plus to form the alkene, two-step process. Okay, again I repeat. First step, removal of leaving group to form the carbocation. Second step, removal of H plus by the base to form the alkene, two-step process, but here is going to be a single step process. Okay, now how will you decide? How will you, both these are similar compounds, whatever I told you. Now how will you decide, right, whether the reaction undergoes E1 or E2, right? Fine, we can tell that, right? Fine, now you see carbocation is an intermediate, right? Carbocation is an intermediate, correct? So if I have the substrate, if I have a primary substrate, secondary substrate, and a tertiary substrate, say primary halide, secondary halide, and tertiary halide, what you have, whatever it is, right? Now you understand that carbocation is an intermediate in the case of E1 mechanism, right? So obviously a more stable carbocation is what is more favorable, is it not? More and more stable carbocation is what is more and more favorable, right? And I know what is the order of carbocation stability. Obviously I know tertiary is more stable than secondary, secondary is more stable than primary, right? So now if you look at it, this will be the order of reactivity for this particular E1 mechanism. So if you have a tertiary substrate means this is the substrate, right? If you have a tertiary substrate, for sure it will undergo only E1 mechanism because I am going to form a more stable carbocation. Okay, right. Now if I'm going to take E2 mechanism, right, now please understand the leaving group leaves and the base has to come simultaneously. Right, now there the reactivity criteria in E1 mechanism was carbocation stability. Here the reactivity criteria is steric hindrance. Right, so what do you mean by steric hindrance? Steric hindrance is nothing but crowdedness. Right, now you see two things are happening simultaneously, right? So what I have to understand is a less crowded substrate. Again repeat, since I have two things happening simultaneously, the substrate which is having less crowdedness, which is not that crowded, will react faster. Yes, that makes sense, right? The substrate which is less crowded, or I would say in technical words, if I have to say it is less sterically hindered, will undergo a faster reaction. Right, now again if I have primary, secondary, and tertiary, right, we know tertiary group is very bulky, secondary is little less bulkier, and primary is least bulkier, or I would say it is least crowded. Right, so now if you have primary, secondary, and tertiary with respect to E1 mechanism, this would have been the order of reactivity. Okay, why? Because primary is the least sterically hindered and tertiary is maximum sterically hindered. Right, so now you'll be able to decide. If I have a primary substrate, right, if I have a primary substrate definitely it will undergo only E2 mechanism. And if you have a tertiary substrate, that will definitely undergo only secondary. That is, if we have a tertiary, it will undergo only E1 mechanism because of carbocation stability. Now, if you ask me, sir, what happens to secondary, it can undergo both. We will not be able to decide like that. Okay, so if you have a secondary substrate, it can either take up E1 or take up E2. But if you have tertiary, I am going to take E1. If I'm going to have primary, definitely it will undergo only E2 mechanism. Okay, did you understand everything whatever I said? Hello?
Yes, sir.
Did you understand everything? Is there any doubt whatever from whatever I spoke?
No, sir. It was clear.
Yeah. What about others? Did you understand, guys?
Yes, sir. It's clear, sir.
Okay, fine.
So once,
yeah.
could you again explain how to decide, sir?
Okay, so okay, fine. So in E1 mechanism, what you see is there is a carbocation. Okay, now the substrate, based on the substrate only, I will be able to decide whether that undergoes E1 or E2 mechanism. Right. So in E1, you see that there is a carbocation formed. Right. Now, obviously, among primary, secondary, and tertiary cases, tertiary carbocation is very stable. Right. So now, if I have the substrate to be a tertiary substrate, say for example, if this was CH3, and there's another carbon and there is an X, there is a functional group, right? So this is a tertiary carbon atom, then tertiary alkyl group, whatever is there. So obviously that will undergo only E1 mechanism because if it undergoes E1 mechanism, I'm going to have more stable substrate, more stable carbocation, that is tertiary carbocation. That's why. Now, if I go for E2, now there the criteria for reactivity is stability of carbocation. Obviously, tertiary, if I have, definitely it will go undergo E1 mechanism. Right. Now, if I have E1, E2, if this is E2, now what you're understanding is there are two things happening simultaneously, right? So here the criteria for reactivity is steric hindrance, that is crowdedness, right? So what you have to understand is lesser crowded species will undergo faster E2 mechanism. Again, I repeat, lesser crowded substrate will undergo faster E2 mechanism. Right. Now, if I compare primary, secondary, and tertiary substrates, right? So you can easily say that tertiary will be very, very crowded because I have 3 carbon atoms attached to that. Secondary will be less crowded, and primary will be the least crowded. Correct, right? So obviously the least crowded one will undergo the reaction faster. So in this case, primary, if I have a primary substrate, definitely it will undergo only E2 mechanism. And if I have a tertiary substrate, it will definitely undergo only E1 mechanism. And if I have secondary, that depends on the reaction. We will not be able to decide like that. Yes, understood?
Yes, sir, understood.
Okay. So that is about elimination, but we are going to have so many other types of elimination that we'll see tomorrow. Tomorrow morning you will have 7 o'clock class. Till I think Friday you will have before Friday, if I complete everything along with S&P S block, then I'll leave you before Friday itself, right? But most probably you will be attending Monday to Friday. You'll be attending all the classes from 7 to 8 in the morning. Okay, and by this Friday I will be completing your portions. Right. So I heard that you're going to have some pre-board exams or something you're going to have, right? So I think that is 1 week after that, 1 week after Friday. So you have 1 week to prepare. Okay. So in that meantime, after I finish the portions, if you have any doubts, you can call Akila ma'am, or you can call any Epsilon management, and you can ask for an extra class. Like you can ask me your doubts, and maybe I'll be able to help you whatever possible.
Okay.
Right. So we'll stop this for today, people. Okay. So tomorrow we'll meet again. We'll see what are, now this is just a mechanism, just an overall sketch. This is what actual reactions we'll see tomorrow. Okay, fine. Thank you so much. We'll meet tomorrow.
Thank you, sir.
Yeah. Thank you.
Yes, sir.
Yeah.